Okay, and lastly, to do comparisons, as we'll need to do often, just quickly throw at you the percent error equation. So if you haven't done this before, percent error, lower symbol delta, is simply a percentage value that relates the difference that you have between an actual value and the expected value divided through by that expected value. Okay, so we have the difference between observed and expected as the numerator divided through by the expected value and multiplied by 100%. This is a useful way to compare data to actual, like we saw in the upper and lower bounds in the property averaging slide for modulus. Clearly we have a predicted value as an upper bound, and perhaps an actual realized specimen might be a little lower than that, and we could determine the percent error this way. Okay, so let's do another experiment or example here where we calculate the isostrain modulus of epoxy reinforced material with 73.3 volume percent E-glass fibers and compare it to the results that we measured in the value in table 12.7. Okay, so see if you can take a minute to calculate the modulus here with 73 volume percent E-glass for an epoxy this time. And resume the video when you've had a chance to try this question. Okay, well, let's start with what we know. We know that the volume of the fibers, volume fraction of the fibers is 0.733. We know that the volume fraction of the matrix, which is epoxy, is going to be 1 minus 0.733. We also know that from the earlier table that the modulus of the fiber was that 72.4 times 10 to the 3 megapascals, and that the modulus of the matrix for this epoxy now was 6.9 times 10 to the 3 megapascals. And so a very similar question to what we had before. The modulus of the composite here is going to be 1 minus 0.733 times the modulus of the matrix here at 6.9 times 10 to the 3 megapascals plus 0.733 times the 72.4 times 10 to the 3 megapascals to give a modulus for the composite here of 54.9 times 10 to the 3 megapascals for that of the composite. Okay, so from your textbook, the comparison we need to make now, that's over in 12.7, tells us that we should expect this composite to have, so let's call this the actual, I'll give an A, and we'll give this the experimental E. The actual value here is 56 times 10 to the 3 megapascals. And so the percent error, to do our comparison here, is going to be 56 times 10 to the 3 minus 54.9 times 10 to the 3 megapascals divided through by the actual, which is the 56 times 10 to the 3 megapascals, times 100%. So our percent error in this case is 2%. So our actual specimen is out of spec with respect to the actual of about 2%. Okay. Good. And so you see that also formalized here in your table nicely, in your textbook nicely for you. And lastly, we'll talk about laminates. Here what is done is often stacking stacking and bonding of fiber reinforced sheets is applied here to make a laminate. And so some of the composites that we've discussed earlier, like PMCs, can be stacked. So this could be an individual PMC here, and this could be the next PMC here, etc. And we can choose to reorient these so they don't have to be in the same orientation. They can be at orthogonal angles between each other. And ultimately, this is a way to benefit from properties that are ideal along the length of fibers, and we can position that in the next laminate structure that is below and spread out that beneficial property into two or more directions by doing a sequence that is offset from one another. So this is how we achieve quasi-isotropic. So the property is near the same by way of making this laminate. So isotropic property, the same in all directions. Anisotropic would be different property that is directionally specific. Also, one can make sandwich panels. So what one tends to do here to make ultra lightweight, strong materials is to use a core material is very light. So here this is often a honeycomb type structure that you see here in the pink structure, where in the space that is in the honeycomb area, so the little tunnels, these would be air, so therefore very light, and the structure along the length of it might be something like a Kevlar or polymer matrix of some sort. And that core structure would have adhesives on either side to allow bonding with face sheets, some of which could have their own laminate type structure like long length fibers in a polymer matrix. And so an ultimate sandwich panel type structure like this has a lot of benefits in that it's low density given the inclusion of air in the core material, and can be very stiff given that any bending that would have to occur would have to distort not only the top plane in tension, but compress the bottommost plane and transmit that through an orthogonal media like this honeycomb core structure in the middle. Okay, and then to just touch on some final manufacturing approaches for working with these materials, we saw earlier the difference between thermoplastics and thermosets. And so thermoplastics, where we are not cross-linked or not network bonded, we can typically do injection molding, extrusion molding, and blow molding. And in the area of working with thermosets, compression molding and transfer molding is typically done. And these same ideas are often used for working with composites on thermoplastics and thermosets as well. So here's a wet layup, hand layup type approach where a mold, shown in kind of dark gray, would be used. Release film or gel coat is applied, and then a fabric of fiberglass could be applied to that. And then a quantity of liquid resin is kind of poured onto that, and a hand roller, as you can see here, is used to remove voids and spread the resin evenly throughout the fibers. A new layer of fabric would then be applied, and this is an opportunity to reorient that to make fibers point in an orthogonal direction if we wanted to achieve quasi-isotropic properties. More resin could then be applied and rolled and repeated again and again. And ultimately, the full material then needs to be cured by either heating or exposing to light to trigger further polymerization or bonding. And much of this can even be done at atmospheric conditions. And some curing methods actually take advantage of triggers from atmospheric conditions. And so ultimately, the purpose of the release film or gel coat is to allow for recovery of the part and debonding, if you want, from the mold. Vacuum bagging is also known. So here, vacuum bagging can be used to improve the quality of composites versus the wet layup method that we just saw. So the vacuum bagging approach benefits by using forces from the atmosphere to apply pressure to spread resin throughout the laminate. So here a bagging film is placed around the laid up composite that we just discussed. So fibers and resin and fibers laminated, laid up by hand. And it would be secured to the tool surface with sealant this time. Okay. And air would then be evacuated from the bag. So you can see here the bag has been applied kind of here, and sealant is used to make a seal between that bag and the ultimate tool. Here's the outermost surface of this bag in cross section, and again sealant over here to bond it. And this stem here is connected to vacuum, so we can evacuate all the air out of here, drawing out all the air. And ultimately, the force due to atmosphere, about 1 atmosphere pressure, if it's a typical space near sea level, would be applied onto the surface of the vacuum bag to press and infuse resin into whatever fiberglass fabric would exist. So this ends up forcing resin into any remaining voids and helps ensure that an even distribution exists for getting that matrix to infuse into the fiberglass fabric that we would have. So this is beneficial because very high viscosity resins can be used, which would be very difficult to hand roll like we saw in the previous hand layup approach. Filament winding is sort of related to this, where there could be a fiber spool. This could be carbon fiber. And this material would be first drawn into a roller-based resin impregnation bath. So here's where we would apply, for example, epoxy resin or other thermoset type materials. Would be drawn through a roller and then out and then over through a carriage, which is programmed to travel along the length of a mandrel, which is spinning and re-spooling, if you want, the fibers that are now wet out with epoxy and sort of built up to make the ultimate cylindrical type structure. So ultimately, once the mandrel is covered with sufficient thickness of fiber, the mandrel can be removed and from the machine while the resin undergoes its full cure, either at atmospheric conditions or UV light or even with heat. The ultimate solid composite, which is largely a spool of the resin plus the fiber, can be taken off the mandrel, and in some cases the mandrel can even be dissolved away if necessary. So these structures, ultimately, these sort of cylindrical type structures, are very good for pressure type vessels like tanks, as the fibers tend to be oriented circumferentially, which provide a lot of hoop strength for that tank. Pultrusion is another approach where, again, fibers are pulled away from a fiber creel or set of spools, and they're pulled through a resin bath again. So here you see it in cross section if it was unclear on the previous slide. And they ultimately pass through a preformer, which can align those fibers into the required cross-sectional shape. And the forming and curing dyes ultimately finalize the shape of the composite and remove any excess resin and the cure of the composite so that it can be cut into sections as needed, ultimately here with the cut saw that you see here. So ultimately, the puller mechanism here is what's drawing resins out in this pultrusion mechanism. Okay, and then resin transfer molding. Here, this technique is often used when there's low volume production needed in the manufacture of components, such as boat hulls or car parts, etc. So generally, maybe only one or two of these are needed per unit time. If you needed to do high throughput, you might choose a different technique. So here, there's an upper mold and a lower mold, which can ultimately be separated. Clamps are holding those together, and there's a cavity where a resin injector is applied. And two-part resins like epoxy part A, base, and epoxy cure agent part B could be transferred and mixed and into the cavity of the mold. And of course, the mold has our dry woven fiberglass material shown as the dotted line here in cross section, and this would be a way to make a laminate. A composite of fiberglass and epoxy resin, for example. And we've seen compression molding as well. This is another approach that can be used for handling polymer matrix composites, where a charge is applied between two plates that are acting as our mold, and provided that the tool's definition is compatible with the ultimate distortion of the fiberglass resin composite, and that we can use this technique for short cycle time, we can therefore achieve kind of higher throughputs to make sure that the technique is, can make more than a couple parts per unit time, for example. Okay, and we mentioned again, for lower volume production, the high machine costs here might make this process prohibitively expensive. So, the motors to ensure the compression and the molds, etc., this can be very expensive. So it may not be ideal for all manufacturing approaches. Okay, so I think we'll end there. That was our lecture on composites.